Welcome everyone. Very happy to see many of you today for Steve Awodey's talk, who is visiting us from Carnegie Mellon University in Pittsburgh. So Steve is a major figure and has done big achievements in category theory, categorical logic, realizability type theory in particular, homotopy type theory. You also have a connection to philosophy of math. So Saunders MacLean, one of the co-creators of category theory, was your PhD advisor. Yeah, with that being said, we're very much looking forward to your talk about what is HoTT.
Great. Thank you, Jonathan, for that generous introduction, and thank you for the invitation. It's a pleasure to be here. We get to meet some people whose names I know, but who I didn't meet before, so that's wonderful. Well, this is being recorded. Got it. And I'm pleased to be able to explain to you something about HoTT, which is homotopy type theory. Maybe some of you already know something about it, but I'm going to kind of start from scratch and explain to you what is homotopy type theory and what is it for, and then try to bring you a little bit up to date with some of the recent advances that have been made and some of the challenges that we're working on. So, homotopy type theory is a new field of study. It's based on a connection between, on the one hand, logic, in particular Martin Löw's constructive type theory, which is a system of foundations, and on the other hand, topology, and in particular homotopy theory in topology. The constructive type theory was originated with a kind of a principled motivation derived from the notion of constructability and maybe consistency in mathematics with a proof theoretic bent. And but it turned out very soon to have connections to computer programming and computability and systems, later systems of formalization in mathematics. And now it underlies some of the principal computer proof systems for formally verifying mathematical theorems, like Lean and Koch and Agda, some of these systems. So there are strong connections on the one hand in homotopy type theory through Martin Löw type theory to computer formalizations. Here, that's what I'm saying here. It's a constructive system, and it has these applications because of its constructive character. And as such, HoTT allows us to use these systems to formalize, there we are, right? It allows us to use these computer proof systems then to formalize mathematics that is not simply elementary mathematics, not algebra, constructive analysis, things like that, but also higher mathematics because of the connection to homotopy theory. Homotopy theory is closely related also to category theory and higher dimensional category theory. Higher infinity category theory is in part motivated by applications in homotopy theory. So this connection that exists in homotopy type theory between constructive type theory and homotopy theory allows us to use the computer proof systems to formalize results in higher category theory and in modern homotopy theory. So that's one of the appealing aspects of the program, and I'm going to tell you later on some specifics about that. One of the original motivations of the type theory, of course, was the constructive character, and that's what has driven the applications in computer proof systems. But now the connection to homotopy theory begs a question, which I'm going to emphasize now in this talk, of whether it preserves the constructive character of the type theory. And the answer is going to be yes, and it'll take us a little while to get there. So type theory, extra credit if you can identify all four. Who can identify all four type theorists? Go ahead.
Gregor, Russell, Martin Löw, Gödel.
There we are, Frege,
Oh,
Russell.
wow. That's
Yeah,
impressive.
8:30.
You go to the right? Yeah.
Nice picture of Frege.
Clockwise.
Good picture of Per Martin too at Oberwolfach. So the constructive type theory, which goes back to maybe Bill Howard, Per Martin Löf, Bill Tate. Also, I think an early figure in this connection is Dana Scott. Replaces the logical formulas of the Frege, Russell, Gödel tradition with types. And the types in the type theory are constructed by some type forming operations, which replace maybe the logical operations on propositions. So the idea here, which I'll describe a little bit more detail soon, is that the propositions and the predicates and the formulas of predicate logic are replaced by types. And these types, unlike formulas in predicate logic, can be not only true or false, but they can have terms, and they can have possibly many different terms. So this adds a new dimension, if you will, of what the proof theorist calls proof relevance. So a type can be inhabited by a term, and indeed it can be inhabited by many different terms. And you think of the terms maybe as witnesses of the truth, or proofs of the proposition, or grounds of truth, or methods of verification. So it adds another aspect to the logic that's expressed by the type theory. So here, can you see if I drive around with my cursor?
Yep.
Okay, good. So, for example, the type n of natural numbers will have as its terms expressions for natural numbers. The type 0 won't have any terms at all. It's the empty type. The type 1 has a unique term, which I'll write here as star. Let's go over here to the product type, has as its terms pairs of terms, one from A and one from B. The distinctive function type here, which is the type of all functions from A to B, has as its terms things that express a function that takes arguments in A and returns values in B. And this is the lambda abstraction notation, which you may have seen in the lambda calculus. Actually goes back to Frege, the idea being that if B is a term of type B, possibly containing a variable x of type A, then the expression lambda x of type B of x represents a function which takes arguments, which could be plugged in for the variable x, to values, which would come from evaluating this term B at the argument x, or the argument A of type A. So that's the type of functions. In addition to these basic simple types, there are what's called dependent types. A dependent type can be thought of as a family of types varying in a parameter, which itself is from another type. So here, if I have a variable x of type A, I can have a family of types, B of x, which vary in that parameter. So that's the idea here. This turnstile is doing a different job than it does in predicate logic. Here, it's just acting as punctuation, which separates the context here of variables from the type itself. So this is a family of types, B of x, varying in a parameter x, which is indexed over a type A. That's the idea of dependent types. And now once I have dependent types, there are new type forming operations. And these are the sum and product type, for example, replacing these simple type forming operations by acting on a family of types and giving me here, for example, a disjoint sum, maybe of all the types in the family, or a total variation. And here is a product of all the types in the family. That's the product type constructor. So those are kind of the basic constructions. A term now of a complex type like this can be unpacked in terms of these constructors. So here's just an example. If I have a term of type pi over the A's and sigma over the B's, and then this is a type family in two variables, this term determines a computable function because it takes arguments of type A to values that are in the type B. And this computable function acts as follows. It takes an argument A and it returns a term T1 of A, which is in the type B. And then it also returns another ingredient, namely a proof that that term T1 of A satisfies the condition R. So maybe you'll recognize this as something like the axiom of choice, right? It's telling me that if for all X and A, there exists a Y and B such that R, X, Y, then there's a function from A to B such that for all A and A, the function applied to that A is in B, and there's a proof that that pair satisfies the expression RAB. So that's a kind of constructive version of the axiom of choice, which follows from this property that for all A, there exists a B of type RAB. And in fact, that's provable from the laws of the sigma and pi type. And it's part of the constructive character of the system, that the axiom of choice is provable in this form inside of the type theory. So type theory is a very powerful, constructive system of logic, which even involves this kind of axiom choice like
But this is
principle.
this cover all the generality of the axiom of choice.
It's a specific
Oh.
form of the axiom of choice, but it's kind of like a skolemization internally inside the system.
The existence of this term T depends on what the relation R is, right?
Well, if I have this term, well, if I can prove the existence of such a T,
Then
then I can unwind it like
Unwind it
this
like
and
this.
get a computable function. Yeah, but of course, the relation R may prevent me from proving such a T. Okay. But that's an idea, maybe a glimpse of the constructive character of the system. Anytime I can prove such a for all exists statement,
Mhm.
then there's an associated computable function which tracks that for all exists.
What sort of R would prevent that?
Pardon me?
What sort of R would prevent that?
Well,
Yeah.
you might have an R which doesn't have suitable values for arbitrary X. I mean, I have some X, maybe the R is not total on in Y, or it's not total at X. Maybe there are some values of X for which there is no Y. There'll be lots of cases where that could happen.
But sorry, where in the term there is written that Ti is a function, that is that there is only one Y that corresponds to
If I
it.
have such a T, on the one hand, I can evaluate it for any A,
Yeah, that's okay.
and then at the end, there's going to be something left over, and that will be the T2, which is a proof of T1 evaluated at A, that R satisfies the relation. So the terms, for example, of pi type are functions which can be evaluated. So,
Yes, but no, if I read well, the term say T for any X in A, there is an Y in B such that X, Y. But in
Yeah.
order to have a function, I need more than, I need that there is only one Y.
no, it doesn't have to be single valued. I mean,
Okay, so
well, I mean, in this case, you can evaluate the term and you get a value, but then many different values. But
it's a
here,
multifunction.
this no,
No,
it's a single valued function, but it's not, it doesn't have to be unique such Y.
It's
This
choosing.
particular term
It's choosing.
chooses one.
Ah,
That's the
this
axiom of choice.
particular term choose.
Chooses one. That's
Okay.
the axiom of choice. It chooses. If I have a family of types and each one is inhabited,
Okay, okay.
then the term chooses one, each element of the term.
I mean, that's kind of the point, right?
Yeah.
The
Yes.
term T is actually encoding the choice.
That's right.
So
The
proving
choice
that,
function.
so finding the term means you have found a choice function.
Okay,
And you
so
found one choice function.
That's correct.
the choice is encoded by T, not
Yes.
by F. Okay, okay, okay.
So
okay.
my question about R was because in the axiom of choice, we have, it is a universal statement. every time that you have a family that satisfies certain such, you
Good.
find, right?
Yes,
But here, the fact that you can prove that T exists,
yes,
this is telling you that maybe already R was such that the T exists, and so it's not such a universal statement as the axiom of choice.
well,
And
yeah.
it's
Right.
normal. I mean, we should expect that because this is even giving us a computable function, not just
That's right.
So
That's
yeah.
correct. That's correct. So in particular, this sigma type, which we've started reading as an existence quantifier,
Mhm.
which is correct, is a special kind of existence. It's a constructive existence with a dependency involved, right? It's making a particular choice.
Yeah.
It's not just saying there is one,
Yeah.
but there is a chosen one.
There's it.
Maybe a better way of reading it is there is given one, something like that. And that's part of the constructive interpretation of the quantifiers here. Now, okay, so
Mhm.
this note is what we've just been discussing. So this is the constructive version, the type theoretic version of the axiom of choice. And in fact, we've started using this constructive replacement of the predicate logical operations now by the type theoretic operations, which have this constructive character. The product is like a conjunction. The function type is like an implication, right? If I think of the types as propositions, which I can, right? Then these operations on the types are acting as logical operations. The sigma type, the disjoint sum of the family of types, is like an existential quantifier, but it has this extra constructive character. The product of the family of types is actually a type of all cross sections of that family, and that's acting like a universal quantifier. So the logical operations in the type theory are promoted to these type constructors. Now, one of the novelties of, so this is called the Curry-Howard correspondence, maybe you've seen that before. One of the novelties that Paramount and Luff introduced was the notion of an identity type. An identity type, I should have maybe put a subscript here because it's always over a given type. And it takes two terms of the same type and it produces a new type, which is the type of identifications between those two terms in that type. Okay. So it's a new type and it has rules, introduction, elimination, computation rules, which preserve the constructive character of the system. The specialists will say it preserves the normalization property or the canonicity property. The type theory has some very special computability properties, and they're preserved by the introduction of these new identity types in the system. And I'm going to describe a little bit more what these identity types are. But one of the features, which is somewhat mysterious, or at least was, is that because the identity type is itself a type, it may have terms. I told you, you can think of a term of identity type as an identification. Maybe a term P is an identification between A and B. But what if there's another term, Q? What is that? It's a proof that A equals B, but the Q is another proof that A equals B. So what's going on with these several different proofs of identity type? And indeed, if I go on now, I could make the identity type over this identity type of P and Q, and that can have some proofs. So now that I get this infinite hierarchy of proofs of identity, of proofs of identity, of proofs of identity, and so on. And that becomes a very mysterious aspect of this system of type theory. And one of the advances that we've made in homotopy type theory is to interpret this hierarchy of identity proofs in a way that makes sense. Previously, this was a kind of a mystery in the system. In fact, originally it was a defect in the system, it was thought to be a defect. There were adjustments were made to the system, additional axioms were added. It was found that the additional axioms destroyed the constructive character of the type theory, so one went back to the original system with its mysterious hierarchy of identity proofs. And so one of the contributions of the homotopy type theory is to provide an interpretation of this hierarchy of identity proofs, which makes sense of this proliferation of identity terms. And the way we do it is we go back to Dana Scott's interpretation of the simply type lambda calculus, which is what gave us Dana's idea that you can model computability with continuity. And that was a breakthrough idea. It gave rise to domain theory and a great advance in theoretical computer science. Dana's idea was, at least in simple type theory, where you have products and function types, the types are like spaces. The terms are continuous functions between the spaces. And so the new idea that we introduced was that the identity terms should be paths in the space. So let me suggest how that's going to work. So here's maybe a type A and a term, let's say A of type A. So the idea is A is going to be a space, and a term is going to be a point in the space. And if I have another one, here's B, then I can build, so here's another one, right? Here's B. Then I can build the identity type, and I told you it should be indexed by the type. And now what if I have a proof that A equals B? The interpretation now is not going to be the proof theoretic one, that there's some natural deduction or something like that. Instead, it's going to be a topological one, and the interpretation is going to be a continuous path P from A to B. Continuous function from the unit interval 0, 1 into the space A, which takes 0 to little a and takes 1 to little b. That's the interpretation of these paths, of these identity proofs in terms of paths in the space A. So that's the new idea. And then a dependent type, remember, it's my notation here, A, B, a dependent type over A. We have time, right? Didn't we say that there's plenty of time here? A dependent type over A is a family of types varying over a type. So up here, there's some big space and it's projecting down, and over each point, there's a fiber, and that's B at A, and this is B at B. And now the interpretation of a dependent type as a family of types varying in a parameter is not just a disjoint sum of all these values, but it has to have an additional property, namely, it has to respect the paths. So if I have a path down here, P from A to B, there has to be a way of taking something here, some X, over to something here. Some, let's say it's P acting on X. Well, in fact, it's going to be a whole path up here. So this is exactly the path lifting property from topology, which says that this is not only a continuous function, but it's actually a fibration. And that follows from the rules of the type theory. So this was a key insight, is we can interpret the identity proofs as paths in a space. And it follows from that that the dependent types, right, X of type A, dependent family B of X, is interpreted as a fibration. The fibration means it has the path lifting property. I'll say a little bit more about the interpretation later, but this is the basic idea from which everything else follows, is that the identity terms, the proofs of identity, are paths in the space interpreting the type.
Is that just for identity proofs or any proofs that you can interpret those?
So this is the terms, any term of a type is interpreted as a point of the associated space. If the type is an identity type, then the point is a point of the path space, and therefore a path in the space.
I mean, you can have other proofs that are I don't know, implications, which would then be functions. So I mean, this is just talking about identity.
In the previous slide,
Yes.
you mentioned this interpretation. How far should we take this, the meaning of interpretation? Is it a metaphor? Is it?
Yeah, thank you.
There are models. What
Thank you.
is it?
Yeah, not, it's a formal semantics for the system of type theory, which satisfies all of the rules strictly. It's a theorem
I see.
that the system of type theory with identity types and sigma and pi has formal semantics in the category of homotopy types of spaces, and that can be made.
And actually,
Sorry.
and actually, it's much more general than that. So you could take any homotopy theory, so not just the homotopy of theory of
Yeah.
spaces, but
That's right.
any higher sheaf category. So that's so Mike Schulman is the one who proved it, like in full generality a few years ago, that this really goes like a very long way in a very precise sense.
Yeah, in the kind of modern homotopy theory, one doesn't just look at topological spaces, but one looks for simplicial sets and then equivalent model categories, and then simplicial categories of simplicial sheaves and so on. And there was a whole range of different homotopy theories for in different settings, all the way to algebraic geometry and beyond. And in any equivalent model category satisfying the usual conditions, you can interpret the Martinov international type theory with identity types. In fact, that's the way the interpretation works. It uses the laws of equivalent model, which is kind of axiomatic description of a homotopy. So let me just kind of unwind the specification a little bit more. If we have the usual laws of identity that you know from propositional or predicate logic, then maybe you know the reflexivity and the symmetry law. If A equals B, then B equals A. Well, if we decorate these laws with proof terms, right, then the reflexivity becomes a path from A to A in the space. The symmetry becomes an inverse of the path going back from B to A. The transitivity of equality becomes a composition operation on the paths in the space. Moreover, paths themselves satisfy higher laws. So what are these higher laws? If I have a path like P, and then I have an inverse, well, then I can compose P with P inverse. Now, I don't get the identity at A. However, I get something which contracts to A or is equivalent to A or is homotopic to A. And so there's a higher notion of homotopy. If I have a space and I have a path here from A to B, I think this is my example, and I have another path here, Q to C, and then I compose them up, I get QP. Then if I have another path here to D, and I have PQR, then here's RQ. Well, then if I compose around this way, right, then that's the same if I first compose this way and then compose with R, or if I first compose this way and then compose with R. And there's a law that relates those two things, and here it is. It says that P after Q after R is double wiggles Q after P after Q after R. What is this double wiggles? It's a sort of higher identity between the two paths. Now, how are we going? So if I write this in type theory, it's going to be a higher identity type. It's going to be something like this. I take id at id A of AB, right? And then I have some P here, and then I have some other path Q, and then I might have some higher identity term alpha. So what is that? What is the interpretation of such a high? This was I told you, the proliferation of higher identity terms. Well, don't have to figure it out. The homotopy theorists already know what that is. If I have a path P from A to B and another one here, Q, I know what it means to have a path from P to Q. It's a continuous deformation of this path into this path. So an alpha is a homotopy from P to Q. Just like in homotopy theory, I have these two paths and I have a continuous deformation of one path into the other. You can imagine that as a kind of sheet. It fills the space between P and Q. There may be one, there may not be one. It depends on the space, right? There could be a hole in here and then I can't make such a transformation. That's a obstruction. In fact, now that we have this idea of homotopies, we know how to go on. We know what a higher identity is between alpha and some other term beta, right? There could be a higher identity type here from alpha beta. And that could have some terms here, phi. So that's going to be, the beta is going to be another sheet like alpha with the same boundary. And then the phi is going to fill a sphere or something homotopic to a sphere between the alpha and the beta. So the higher laws of identity, like this sort of associativity of transitivity, are nothing but higher homotopies. And the laws of homotopy theory already tell us how these things behave. In fact, the higher identity types in the type theory endow each type with a higher structure, points, paths, homotopies, higher homotopies, and so on, which is something that already is known in homotopy theory. It's a naturally occurring, if you will, mathematical structure. It's popping up here in intentional type theory. It already popped up in homotopy theory, was discovered by Grothendieck as part of the homotopy hypothesis, which is a classification of the homotopy types of spaces in terms of what are called infinity groupoids. An infinity groupoid is a higher dimensional categorical structure in which every arrow is invertible, and you have arrows between arrows and arrows between arrows between arrows and so on. It's a naturally occurring mathematical structure. And here it is in the foundations of mathematics and the constructive foundations of mathematics occurring in the intentional type theory of Martin Löw. This is a theorem that was proved in 2006, I think. Peter Lumstein's dissertation was 6. We haven't done anything yet to the type theory. We're just investigating the type. We're using the rules that Martin Löw proposed, and we're discovering this structure inside the type theory of higher infinity groupoids.
Sorry, just a curiosity at this point.
Yeah.
A pair made something in his joy. Martin Löw is doing something or has done something in HoTT apart the original theory, has been active in this domain or not?
He's monitoring our progress.
Okay.
He's very interested
This is
in it.
Bob.
He's very interested in it. He was at I'm going to tell you in a minute about a research program at the Institute for Advanced Study in Princeton that happened about 10 years ago. And he was there for some of it. And he was very interested in what was happening. He hasn't made any contributions to the homotopical side, but he's certainly fascinated by it. And he's contributed questions. Let's put it that way. So,
and I know his questions are not easy.
one thing that happens now is we've discovered that every type in the type theory has this structure of an infinity groupoid automatically from the tower of identity types over that type, iterated identity types. Now, it happens that for some types, that infinity groupoid is degenerate at some point. For example, it may be that any two terms have an identity proof that relates them. It may be that any two identity proofs have a higher homotopy between them, and so on. And in terms of that structure, one can classify the types. Indeed, the types of the type theory are naturally stratified by what we'll call the homotopical dimension, what the homotopy theorist calls the truncation level. There are n types, there are 1 types, there are 0 types, and propositions, and so on. So a type, and these are conditions that can be written down in the type theory. Here's a kind of recursive specification of the higher types. And this is then a refinement of the propositions as types interpretation due to Permont-Lev, according to which proposition is interpreted as a type. Now, instead of the types being regarded as propositions, the types are higher structures. They're groupoids, infinity groupoids, which may have more than just a truth value that is inhabited or not, and more than just a set of all the proofs. That's the propositions as types interpretation that I talked about yesterday. But there's a whole infinity groupoid of proofs with all of their higher structure. So the universe of mathematical objects, if you will, the universe of all types now is a two-dimensional system of, on the one hand, the hierarchy you may be familiar with from set theory or predicate logic of size, where things get bigger and bigger, like in predicate logic with higher and higher power sets, but also homotopical dimension, which is independent of this old axis that you may have seen before. Now there's the homotopical dimension of structure, the homotopical structure of the types. And this is something that Voevodsky discovered, Vladimir Voevodsky. And in this connection, he proposed his univalence axiom, which you may have heard of. And what the univalence axiom tells you or asserts is that in a universe of types, one of these levels here of size, there are types of all different dimensions, and the identity type on the universe, which has paths between the types in the universe, is itself equivalent to the equivalences between those types. Now, equivalences between types is again a notion that's definable in type theory. It's a generalization of isomorphism of sets, which is coming from homotopy theory. And it captures the idea of two spaces being homotopy equivalent, which means there's a map one way and a map coming back. And if you compose the two maps, you get something that's homotopic to the identity on that type. So it tells you that one type can be deformed into the other one in a continuous way, maybe without tearing it, something like that. So it's a generalization of isomorphism in the sense that it doesn't preserve cardinality. It doesn't preserve the cardinality of the underlying set of points of the space. So for example, a solid ball is homotopically equivalent to a point because you can contract it down to a point. So that certainly doesn't preserve cardinality, but it's a kind of equivalence. It's equivalence up to homotopy. And what Voevodsky asserted, and it's an expression that can be added to the type theory, is that two types are equivalent just in case the identity type on the universe relating them is inhabited. And moreover, the identity type between those two types is itself equivalent to the type of equivalences between those two types. So it's a kind of subtle notion, but it can be read as saying equivalence is equivalent to identity for types. It's a kind of invariance principle for type theory, which says you can identify equivalent types. Yeah, that's what this is saying. You can, the identity type between two types can be identified with the type of equivalences between the types. So it's a kind of isomorphism invariance, if you like, but up to homotopy. It has remarkable consequences in the theory. It's a principle that can be added to the type theory, to Martin-Lev type theory. So this is the first time I've talked about adding anything, right? Before it was just interpretation. Now every type has an identity type. It has some rules. The universe of all types has its identity type. And here's a proposal for an axiom which can be added to the type theory, which identifies the identity type with the type of equivalences between the types. It's a radical idea. It turns out it's consistent. Blavatsky gave a model of it to show that it's formally consistent. And the model is actually the kind of canonical one, I would say. It's the model in the homotopy theory of spaces. The homotopy theory of spaces, Blavatsky uses Kahn simplicial sets to model spaces, but that's what the modern algebraic topologist does. He proved that the universe of types in the Kahn simplicial sets in the standard Quillen model structure, Kahn Quillen model structure, satisfies this.
Who is
So the
a
axiom is true of homotopy types of spaces.
is a proof of equiconsistency with set theory. So the model is constructed in set theory.
The model is constructed in set
So
theory.
what is proved that the action is equiconsistent with set theory.
Well, it's consistent with set theory. It uses actually set theory with an additional inaccessible cardinal in order to verify this axiom. So that's the one step that we're going to make to add to Martin-Löf type theory, this univalence principle. It strengthens and indeed forces the homotopy interpretation of the Martin-Löf type theory. The bare Martin-Löf type theory is agnostic with regard to this principle. If you put it in, it forces that homotopical interpretation of the type theory. But what about constructivity? That was the kind of driving engine originally of the Martin-Löf type theory. That's what the computability relies on. That's what the modern proof assistants make use of, is the constructive character of the type theory. Now we're fiddling around with it and throwing in some new principle. Per Martin-Löf saw that, he said, no, you can't do it. It destroys the constructive character of the type theory.
Right, just to clarify my
Please, yeah.
previous comment, so it was Steve and a student, Michael Warren, that I think up to a little bit before 2006,
Yeah.
2006.
Yeah.
So you showed that just Martin-Löf type theory with identity types, no universes, no univalence, can be interpreted in just any Quill model structure, which is the technical term for abstract homotopy theory, essentially. So not just the abstract homotopy theory of spaces, but just any abstract homotopy theory according to a certain definition that is widely used in actual homotopy theory, since equivalent. But then when you add universes, so it's not clear that any model category has to have them at all. So then it becomes more complicated, and that's when you get kind of more interested in a somewhat more restrictive class of models, which basically turns out to be these higher sheaf models. And you made this internal language conjecture that just how kind of intuitionistic higher order logic is the internal language of kind of one categorical topos, maybe homotopy type theory, including that univalence axiom should be something like the internal language of higher toposes, higher sheaf toposes, and that actually also turns out to be true in that generality. So it's not just those Kahn simplicial sets that also satisfy the univalence axiom, but this wide class of higher sheaf toposes.
Yeah, that's correct. Thank you, John. Yeah. So what about constructivity? So I'm going to tell you now something about constructivity and what we've learned about the constructive character of the univalence axiom in the 15 years since we started studying it. So one thing that we can do in the type theory is we can axiomatize a class of inductive types which represent certain topological or homotopy types of topological spaces, like the spheres, right? The circle and the two-sphere and three-sphere and so on. We throw them in to the type theory as inductive types, just like we throw in the natural numbers and type of lists and other basic types. We axiomatize them in the same way that the type theorist axiomatizes other inductive types. Here we say, for example, the unit circle is axiomatized by saying it's the free type generated by a point, the base point, and a loop on that point, right? So that would be a term of type, identity type over the circle from base to base. So it's a loop like this. So, and it's the free one that tells you what the rules are for eliminating out of it. And that is an axiomatization of the one sphere as a homotopy type in type theory. And now, given these things, one can consider iterating that loop and going backwards on the loop and composing and so on. And what you get is a group structure. In fact, not only on the one sphere, but on any space, you take any point, you look at the loops on the point, and that's a group. It's called the fundamental group, something that topologists have been studying since Poincaré. The fundamental group of a space at a point is the set of all loops at that point, together with their composition operation and their inverse operation. That forms a group. That's a fundamental group. In homotopy type theory now, we can define that group for any type and for any point in the type. So for example, for the unit circle that I just showed you, introduced as an inductive type, we can ask, what is the fundamental group of that unit circle at the base point? And this was the first proof of concept. It was done in 2011 by Michael Schulman. He proved that the fundamental group of the inductive type, the unit circle, is the integers, just like in classical. The classical result that the fundamental group pi1 of the unit circle S1 is Z, the integers, was proven in Martin-Liv type theory and formalized in the proof assistant. At the time it was called HoTT. And so this was the first computation of a homotopy group of one of the spheres, the simplest homotopy group of the simplest sphere, but nonetheless, it's a start. And it's a proof of concept. It shows that we can prove in type theory. It uses the univalence axiom in an essential way, which I'd be glad to explain to you. And it proves that the circle defined as an inductive type has the correct homotopy. And it's just the start of a whole series of such investigations of higher homotopy groups of higher spheres. Pi k is the kth homotopy group of Sn is the n sphere. We can define them all in homotopy type theory as a kind of logical construction. And we started in the special year at the Institute for Advanced Study. There was a special year on univalent foundations organized by Vladimir and Thierry Coquin, the computer scientist, and me. And we started using computers and this interpretation and the univalence axiom to compute homotopy groups of spheres. The computation of homotopy groups of spheres is a kind of test case for the homotopy theorists. They use this as a test of methods. One of the breakthroughs was J.P. Sayre's dissertation, where he invented spectral sequences in order to compute homotopy groups of spheres for all the pi k of Sn for all the spheres. I'll tell you something about that later on. But it's a kind of a, it's a whetstone against which the homotopy theorists sharpen their tools. It's computing homotopy groups of spheres. So it was a very natural challenge for us to start computing these homotopy groups. And we did it at the Institute here during this special year. So here, extra credit for people who can name all of the, I think Jonathan already got them. He sent me an email ahead of time. I sent him the slides and he recognized everyone here. Some of you may know Bas Spitters, Peter Lumsdain, Andre Bauer, Egbert Reiche.
Who's sitting on the bench on the outside?
I think that's what,
Is that
Jonathan
Martin?
asked. I think, no, I
Martin
think
Escardo? It looks kind of like it might be.
Martin Escardo, yeah, could be, although I thought maybe Matusozo, but I agree that it looks like Martin Escardo. So this is,
He's humped over a laptop, so it's likely to be Martin.
oh, if you saw the movie Oppenheimer, you remember a scene where Oppenheimer goes to the Institute and he goes through this room, he goes charging out these doors to find Einstein out of the
Yeah,
pond.
yeah.
You talk to him, they forgot to remove the bust of Einstein. Anyway, by the end of the special year, one of our brilliant students had computed pi4 of S3. It's the first homotopy group that has some torsion. It's not just Z or a power of Z or something. It's Z mod n for some n. And the proof produces Z mod n for some n of type nat, but we couldn't compute the proof because we didn't have an implementation of univalence, which was computable in the system. So here's the student, Guillaume Brunery. Here he is giving his lecture at the Institute. You can go to the website of the Institute and see this lecture. And if you go to 1 minute and 1 hour, 40 minutes, 32 seconds, you can see Guillaume point to the chalkboard in this proof and say, so what we get is that pi4 of S3 is equal to Z mod n for this n in a term of Martin-Lift type theory. And this is one very concrete and non-trivial example of why we may want to have canonicity, computational interpretation, because this n is a closed term of type Z, defined with a lot of univalence and higher inductive types. So in a perfect world, if you formalize that in a proof assistant with a computational interpretation of univalence, you can just ask, what's the value of n? And it'll compute the value to be 2. And then you'll know that pi4 of S3 is Z mod 2. So that's the constructive character that I told you in the beginning. If you have pi, sigma, and so on, you get a computable function. And it's not just a function, it's a computable function. You can compute the value from the proof. So here's a proof. It's a very elaborate proof, but it produces a computable function. It's a closed term, and you can run it, and you can compute the value, and the value in this case will be 2. So what's happened since 2013? I want to tell you now about the progress on solving this problem. So the first thing was we had to get a constructive interpretation of univalence and these higher inductive types that are the spheres. This took 3 or 4 years. Thierry Cocon and some collaborators developed a constructive version of homotopy type theory, which implements univalence in such a way that, at least in principle, it would compute the values. It would be in the sense of the type theory is a strongly normalizing system. So every term has a normal form, which is the value of the term. Then over the next several years, I guess it's like 3 or 4 years here, 5 years, a new proof assistant was developed, not the version of Koch that we had kind of hot-rodded to do these calculations, but didn't implement univalence. The new system is called cubical AGDA, and it computes with univalence. And up until about 2019, this system was in development. And then it took a long time to implement Guillaume Brunery's proof in this new proof assistant. So the proof that Guillaume gave at the Institute, which said pi4 of S3 is Z mod n for some n, was then actually formalized in cubical AGDA. It doesn't use a Serre spectral sequence, but it uses some pretty sophisticated methods, including a certain spectral sequence. And it was implemented in cubical AGDA. It took several years. Finally, it was completed. And it took then a few more years to actually run it. We had to run this system on supercomputers, which would time out. It would run out of memory. And finally, we had to optimize the proof, and then it worked. And now it's optimized that it takes about 5 seconds to compute the value of n to be 2. And that was 2022, so a few years ago. So that is a great success story that shows that you can actually preserve the constructive character of the system, including univalence, and use it to compute values. So that's where we are now. Several related projects are currently underway. And one of them, which has just been completed in the last less than a month, it's 20 days or something like that, is exactly what I mentioned before, the Serre finiteness theorem from J.P. Serre's dissertation, which computes all of the pi k s n, all k and n, and produces a computable function, which when you give it a k and you give it an n, will return a value, which gives you the torsion coefficient and then the free coefficient of the kth homotopy group of the n sphere, which is finitely presented. That's Serre's theorem. So, and we now have a proof of that in HoTT, which will compute those values. And that's been implemented. So not only a proof in HoTT, that was done 4 years ago by Reid Barton and Tim Kempion at CMU and Johns Hopkins. But now it's been implemented in this cubical Agnes system by a team of people, I should give their names, Anders Mortberg and Axel Ljungström in Stockholm, and Reid Barton and my student Owen Milner at CMU. And this proof now is done and it computes. I don't know how long it will take if they've actually run some values, but the formalization is done. So that's the kind of current events, the latest advance, at least in this thread of homotopy type theory of computing homotopy groups of spheres. That's kind of a test case. There's been a lot of other work that's been done. I've chosen this one kind of red line to give you to bring you up to speed on one topic, to give you a sense of what's happening in this theory. So here's a summary. The old idea, maybe due to Dana, that computability is modeled by continuity extends to all of constructive type theory, including the identity types, with this idea of modeling identity types as paths in space. The type theoretic constructions then become homotopy invariant structures and theorems. Homotopy invariant, I didn't say much about it, but yesterday in the talk, I did emphasize the fact that the consistency of univalence in the system means that everything in the system is homotopy invariant. Otherwise, if there was something that weren't, you couldn't put in the univalent principle, right? So everything, the type theory itself is a homotopy invariant of a space. Any equivalent space will satisfy all the same type theoretic properties, principles, constructions. So the type theory is a homotopy invariant. The constructive proofs yield programs, computable functions for calculating homotopy invariance in a computational system based on Martin-Lew's type theory. And these calculations of the homotopy groups of the spheres are an example of such a calculation, which is a kind of experimental development which we've been working on. Classical foundations, based on set theory, is actually a subsystem of this constructive system of homotopy types, because after all, a set is just a discrete space, right? And so there's a subsystem of the sets which can be identified within the system as the ones that are zero truncated. And all of classical mathematics of sets is a subsystem of this extended universe of homotopy types. I'm going to give Frege the last word here. Frege says, I'm convinced that my Begriffsschrift, which is a kind of elaborate, rudimentary or proto system of type theory, I'm convinced that my Begriffsschrift will find successful application wherever particular value is placed on the rigor of proofs, as in the foundations of the differential and integral calculus. It seems to me that it would be even easier to extend the domain of this formal language to geometry. Only a few more symbols would need to be added for the intuitive relations occurring there in this way, one would obtain a kind of analysis sequence. So that's, I think, a good summary of exactly what we're doing. Okay, that's it. Thanks very much.
We have 14 or more pages.
These are some examples or possible questions or appendices.
Do you have questions?
Yes.
Yeah.
Jonathan has a question,
What's on page 28?
rhetorical question, I suppose. I can go,
Hi,
I have an
Steve.
example here that I can show you if you want. Okay. Oh, that page 28 is some references. I'll provide the slides and then you can
Yeah.
distribute them if you like.
Yes,
Do you have another question?
What's on page 29?
It's a sketch of the proof of pi one of S1, you know. If you want to see it, I'll show you. How it goes.
Yes, please.
If you don't
Steve.
want to see it, you're free to go now. If you don't want to. So what we're going to do is we're going to take the classical proof from algebraic topology and we're going to implement it in the type theory. And the classical proof does this. It takes the circle, here it is with its base point, and it gives a covering space over the circle, which is this helix, that's infinite kind of winding of the real numbers projecting down to the circle. Okay, so we're going to do that in HoTT. So first of all, what is this thing? This is a family of types indexed over the base, just like this, right? Here's the fiber over the base is the integers. There it is right there. But then as you move around the circle, if you could, you would move around the helix here, go up and up and up, down and down and down, depending on which way around you go. So we have to build this covering space now. I'm going to call it cov, and it's going to have to be a family of types indexed over S1. Remember what the inductive property of S1 is. The inductive property is if I give you some other type, I have to take a point and I have to take a loop in that point, a loop at that point in the other space, and then I get a free function from the circle into that other space, which takes the base point to the chosen point and takes the generic loop in S1 to that chosen loop. So in order to get a covering space like this, I need a point and a loop in the universe, right? So in order to get a map from S1 to U, this covering space, I have to take a point in the universe and a loop in the universe. So that's what I have to give you, and then that will return this covering space. Okay, what will the point be, and what will the loop be at that point in the universe? Well, for the point, I'm going to take the integers, because I just showed you what it's supposed to be. It's supposed to be this, right? That's the integers. So for the point, I take the integers. That's a point of the universe. For the loop, I'm going to use the univalence axiom. What is a loop in the universe from the integers to the integers? The univalence axiom tells me that identity proofs correspond uniquely to equivalences. The integers are a set, a zero type, and therefore an equivalence on the set of integers is just an isomorphism. So I have to give you an isomorphism from Z to Z to be my loop in the universe. And then I'll hit it with the univalence axiom, and that will give me the loop. If I were to take the identity equivalence, I would get a covering space that's just Z many circles all stacked up like this. Instead, I have to have a shift built in, right? And so as my equivalence, I just take the shift by one, add one. And that's an isomorphism on the integers. It's just adding one. So the equivalence is the successor function here on the integers. And now I get my covering space, S1, into the universe by circle recursion, if you will. I take the base point to Z, and I take the loop to the univalence axiom applied to the successor function. That's an explicit expression in type theory that I can write down, and that's my covering space. So there it is. If I want to actually write it down as a covering space in this style, I take the sigma over all the values of that thing and I project it down. That's the first projection from the sigma type down to the circle. So that gives me this structure that I need in order to compute now the winding number. So the winding number of a path down here in the base is defined by this transport operation along the path, which starts and ends in the same fiber, because there's only one fiber here. It's the fiber over the base point. So if I have a path here going around this way, and I have a point up here, then I apply the transport along that path, and it gives me the next level up. And that's the winding number. So maybe the path goes like this, it goes once around. Then the winding of that will just be the successor function. But maybe the path goes like this, it does some crazy stuff all over the place. I apply the transport along that path to 0, and it gives me some other value here in the integers. That's the winding number of that path, is the path applied to 0 gives me an integer. That's a function now, a computable function from the loops on the circle to the integers. And now I have to prove that there's an inverse map. And the inverse is not hard to find. I just take an integer and I take the loop and I iterate the loop that many times. And that is the inverse function of that path. And that pair of maps, wind and this loop iteration, I prove is an equivalence. And now that tells me that this guy over here, which is pi1 of the circle at the base point, is equivalent to and therefore isomorphic to the integers. So that's the proof, sketch of the proof. But you can kind of see how one could do that in type theory. That was the proof that Schulman gave. And then it didn't take long to actually formalize the proof. So here's the original formal proof in Schulman's formalization proof system Keck, augmented by the univalence axiom. And I don't expect you to read this code. I don't want to go through it. But what I do want to point out is that it's not that hard. It's 1, 2, 3, 4, 5, 6, 7 pages. So 7 pages of code, not very dense, short pages of code. So here's the univalence axiom is in here somewhere. You put it in as an axiom. I don't know where it is. It's in there somewhere. 7 pages. Look up the proof in Hatcher's book on algebraic topology. It's not a lot shorter than this.
What the job of the univalent axiom in this proof?
Yeah, go.
It's the way that you turn an equivalence into an identity type. The identity type is equivalent to the type of equivalences. So I use the successor function on the integers, right, to give an equivalence, and then I turn that into an identity proof. And that identity proof is the data that I need for the inductive property of the map from the circle into the universe. Yeah. So
There
that's
is
it.
a question
So the
okay.
formalization is, in the world of formalizations of mathematics, there's something called the De Broglie factor or the De Broglie quotient, which takes the length of a formal proof, maybe in characters, and divides it by the length of an informal proof.
Mhm.
And usually it's in the many digits. This is down to 1. So this kind of synthetic, called the synthetic approach, using the homotopy interpretation and the univalence axiom, is an enormous speed up for formalizations, at least for those that are amenable to this setup. So for example, computing homotopy concepts. Okay, so that's the answer to your question.
There is a question from the web by Valeria De Paiva. Valeria, can you speak?
What's Valeria doing here?
Oh,
No, Valeria
hello.
is there. It's the universe.
I think she is. Hi, Valeria.
Hi, Steve. How you doing?
Okay, I don't know.
Yeah,
I don't know.
Valeria, it seems that
Is it in
yeah.
my machine? or-
no, we don't have sound in the room for some reason, so I'm going to turn on my sound, the sound of my computer.
Okay.
There might be some reverb. So
Oh dear. It's not good. I'll write my question.
okay.
Well, maybe I need to turn up my microphone. Is it me or is it?
No, it is.
Okay. Together are together. I've got Jonathan, I've got Eric Reck, who I went to graduate school in Chicago with, and now I've got Valeria, so I wonder who's next.
Valeria, try to speak.
Maybe my brother is gonna walk in a minute.
Sorry, it's not working for some reason. I don't know.
If I do that,
But she that the question.
Can you read my question so that we don't have too much
Oh, okay.
Yes, can you
feed
turn
off?
it? Okay, I will read
First,
your
she said
question.
it's a great survey.
Yeah.
Thank you.
So the question is, I wanted to know what Dan Licata did in the proof of the fundamental group, please.
Okay, so the original proof was given by Mike Schulman. And then the formalization was first given by Mike. It's this one that you see here. And then Mike and Dan together gave another proof, a simpler one, in the AGDA system. And then there's a paper about that that's written in a very nice, engaging style. It was published in Licks, and that's a joint paper, Dan Licata and Mike Schulman.
And
That was the
Guillaume,
first
right?
published version
It's a
of this.
paper by Guillaume and Dan Licata.
Does that
right?
answer your question, Valeria? And she has
Yeah,
another one.
is it a easier proof
Yeah,
then?
still, Valeria, you're trying to speak, but we don't have sound in the room. Sorry.
Can you write?
it's not that we have not sound, we have too much sound.
Forget it.
I'm
But
so
thanks.
sorry, Valeria.
But what is happening? Because
But
it's
she can
was
write
not-
into the chat, no?
Was not so in the
Can we turn off the loudspeakers here? Then the one.
It's a problem with the room computer. The room computer is not detecting the speakers. So it detects the microphone, but it doesn't detect the speakers. So the room doesn't know that the computer doesn't know that there are speakers in the room.
Because it comes from.
So I could, but the thing is that the room computer is not allowing me to turn off the mic. Technology.
Oh, good question.
The second part of the question is, Dan did a paper with Guillaume Brunery. Was this the simpler proof of mentioned?
I think the paper by Dan and Guillaume is computing the homotopy group of the torus,
Ah.
which is Z cross Z. And generalized story.
Thank you.
They give a very nice proof. There were earlier, much more complicated proofs of this, and then they used the AGDA system to give a nice mediating cycle proof, including homotopy groups of the torus.
Thank you.
Thank you, Valeria, for your question and for your patience.
No, thank you.
Peter.
Nice talk. I was wondering the implementation that you mentioned, which used cubical AGDA and which finally was used to do the reduction to 2 to get the number. Is it also 7 pages, or is it shorter, or is it longer?
No, it's much longer. It's much longer. This is the one that was crashing the supercomputers. So
It's longer computation, but that means also the whole proof is much longer.
but this is not just the proof of pi1 of S1.
Ah.
This is the proof pi4 of S3.
Exactly, yes,
That's a much more difficult proof.
I see.
In fact, if I'm not mistaken, that's also VTT Pitzer.
Yes.
And that uses I think the original proof uses a spectral sequence as well. And that's a much longer proof. But then the implementation into the cubical AGDA system is also a very large formalization project, which only with, in fact, we tried to do it earlier using just AGDA, which has also a computational implementation, but it just didn't go. And finally, it took cubical AGDA and then years and years of work and then optimization to get it to compute.
It's also fascinating, this weird analogy to originally Russell and Whitehead in Mathematica
Right,
took like 200 something pages to get to 1 + 1 equals 2.
right.
We have the
Now you're crashing through some
version of this.
But in this case,
progress.
the mathematics itself is very complicated.
Exactly.
It's not like 1 + 1 = 2 is so simple. Pi4 of S3 is a difficult
Yes.
calculation using spectral sequences and all kinds of sophisticated mathematics.
And in fact, I mean, the proof that you mentioned is a formalization of this,
Yes,
and the original proof hasn't really been formalized in some other system, right? This is the first time it's been formalized.
that's right.
And in a computational way, this is absolutely fantastic.
That's right. That's right. This is kind of, at the same time, it's new mathematics, at the same time that it's new kind of computational implementations. Because developing the mathematics in HoTT requires a new angle or a new approach.
So,
Like this simple example of pi1 of S1, which uses the univalence axiom and a weird inductive principle for the circle and so on. These are new mathematical ideas too, which are motivated by the type.
And cubical type theory is a arguably more complicated system.
Yeah.
Because you pay a price to be able to prove univalence.
Compute the values.
Yeah, so you need more. You need some additional kinds of type formers and that interval.
Valeria say, have a nice dinner, but we are still not at the dinner.
Bye, Valeria. Nice to see you.
Cubical type theory was Thierry Coquin's
Yes.
contribution to getting a consistency with univalence, right?
That's
Before that,
right.
it was not entirely clear that you had a computational
Yeah, computational.
interpretation of it. But now is that still the only extent computational interpretation? In other words, are you sort of stuck in cubical type theory? Or are there other models?
I mean, this. I don't know if you want to say something.
So let's distinguish between consistency and the computational.
Yeah, no, I mean the computation.
Consistency.
No, I know, no, yeah.
But the computational interpretation, the best system that we currently have is the cubical AGDA system or the cubical type theory. There are different versions of cubical type theory out there. There's the Orton-Pitts, which is based on the cubical type theory. Coquin and company have different cubical versions depending on the structure of the cubes, whether there are connections, whether there are reversals, and so on. So there are various variations of this idea of the cubical type theory. And then there's a new approach due to Schulman and Torsten Altenkirch and a couple of collaborators using what they call higher observational type theory, which is also a computer implementation of not cubical, but univalence type theory with normalization. And there might be some other one that I'm not thinking of right now, but so we're not stuck in cubical AGDA, fortunately, because it's not a nice place. The system it's not very user friendly. It's more of a theoretical kind of experimental system. It's not fun to use. Well, it's not everyone's taste. Oh, Eric, I think was next.
So Luke and Eric.
I wrap my head around what univalence means. I do physics.
Okay.
So my understanding is that you're saying that equivalence is equivalent to equality.
Yes, that's right.
And if you make that assumption, you sort of, I would expect that you restrict the domain of what you can talk about. You now only talk about things which satisfy this sort of behavior or something. And for example, do I lose a way to talk about the way in which equivalent things are not identical? Like if I have, can I still talk about that sort of situation?
Well, we're talking about homotopy types. And so I don't restrict the domain of the things I talk about, but
Well, it's an axiom, right?
well, originally it was proposed as an axiom,
Uh-huh.
but later on it was shown that it holds for all the standard interpretations of the system in the homotopical setting, right? So it doesn't hold if I interpret the system in a kind of degenerate way where everything is a set. Right? Then it fails. But if I interpret it homotopically, in model category or in infinity topos, as Jonathan would say, or in simplicial sheaves, or in any of the wide range of homotopy theories, then it holds in all of those settings. And that's what motivates putting it in as an axiom. And then there are these other implementations where it's not an axiom, it's a provable principle. And that's what allows you to compute. Because if it's just an axiom, if you were to throw an axiom into Martin-Left type theory, your computation would just get stuck when it hits that axiom. It wouldn't, the system wouldn't know what to do with it. But these other implementations of type theory like cubical, EGDA, and so on, which allow you to compute, will permit you to compute. So that's not anymore an axiom in that sense. So it doesn't.
Can you still talk about the way in which equivalent things are certain? If I can have an equivalence between things that are not identical. And
Well,
I'm trying to understand.
Identical is identical in the type theory, in the sense of the identity type in the type theory. I'm not saying that they're identical in some metaphysical sense or identical in a set theoretic sense of having all the same elements or something like that. It's a primitive notion in type theory, the identity type.
So I should
And
think
what
about-
this principle says is that that identity type as a space, as a type, as a homotopy type, is homotopy equivalent to the type of all equivalents. So it's maybe a way of saying it is that the identity relation in type theory has been expanded in such a way that it's not just some sort of numerical identity of types, but it includes all the equivalences as well. The whole system behaves as though equivalent things were the same. You can't distinguish them in the type theory. Type theory doesn't, maybe if you want to put it in a negative way, it doesn't provide any means to distinguish between equivalent things.
So can I think about it at the univalence as telling me what identity means in this setting? Is that the right way to?
Yeah, you can think of that. I mean, you're a physicist, you should be happy with identifying under kind of invariance, identifying equivalent structures. Nothing mysterious about that from a mathematical point of view. From a mathematical point of view, you have two different presentations of a group. They present the same group, the same in the sense of mathematical identity, which for groups is isomorphism of groups. That's what's going on here. The type theory, the identity relation in the type theory is that. It's like mathematical identity in this, in the sense that the different presentations, the same mathematical object. Does that work? Like I give you two different charts for your space-time theory as a four-dimensional manifold. I'll give you two different atlases. They're equivalent. That's the same space-time. I don't know what kind of a physicist you are, but maybe that helps. I don't know.
Yeah, thank you.
Eric,
Yeah, I have a very general question. It's not a technical question about it. It's
That's
more
okay.
about the role of homotopy type theory. So the way you describe, and it's like the big thing in the background is I'm interested in the relation between constructivist and classical mathematics and how this fits in.
Yeah.
So the way you described it, you start with constructivist homotopy type theory, and you add the homotopy theory to it and the univalence action. So you construct, it sounded like a complex, powerful new constructivist framework or something like that. Is that right? But then how is that related to classical mathematics? At the very end, you made a quick remark about that. So can you now do classical mathematics? And I'm assuming that's part of what you do. And I know you talked of, so one interest seems to be the computability side of it. So there's a lot of research about that.
Yeah.
Now, but what about the relation to classical mathematics? Is this a new framework within which then to do classical mathematics? And do we understand the relation between constructivist and classical mathematics more or differently going through homotopy type theory?
Yeah, that's an interesting question. That's a very good question. So I've emphasized the computability side because that's important for the formalization in a proof assistant and also for the computation of mathematical homotopical invariants like the homotopy spheres, things like that. But of course, it's a more comprehensive foundational system based on Martin Löff's type theory, which was a system of foundations for constructive mathematics. As you said, we added some ingredients. Most of the ingredients are just interpretation. That's what we added. We didn't really add any new principles. The only new principle we added was univalence, which strengthens the interpretation or forces the interpretation, which before was kind of up for grabs. You didn't have to accept it. But this univalence principle forces us to take that point of view of the system. And then within that interpreted system, there is a subsystem of the sets, which behave like the classical universe of sets, with a few exceptions. One is the sets are structuralist in the sense that they get identified if they're isomorphic. Also, any structures based on sets, like algebraic structures, groups and modules and topological spaces, will be identified under univalence if they're isomorphic. And so there's a kind of structural character. So the universe of sets, or the system of all sets within this new foundational system, behaves in a way that is familiar to the working mathematician who doesn't care about what the elements of the sets are. You know, the real numbers are points in the reals. Doesn't matter what their elements are, but that's so in that sense, it's not traditional set theoretic foundations, but it's set-based mathematics. And that is a subsystem of this system of type theory. When it was proposed by Vygotsky, this univalence axiom, the idea was every set is a homotopy type. It's just a discrete homotopy type. And, you know, if you're a homotopy theorist like Vygotsky, everything looks like a homotopy type. And so sets too. And classical mathematics is a subsystem of homotopical mathematics. And that's what's implemented in this system. It's kind of maybe a homotopy theorist's version of classical mathematics in which sets are discrete homotopy types. So they're identified as isomorphism.
Just to follow up, is this meant to be a new sort of foundation or at least a general framework for mathematics? Theory meant that, or is it just a interesting part of it?
For Voevodsky, it was intended as a new foundation for mathematics. He called it univalent foundations. And the idea was maybe twofold. One is to have a new system of foundations which admits formalization in a computer proof system, which can improve or increase the certainty of mathematical proofs, because he gave several examples of fallacious or erroneous published proofs, some of which were his own, one of which for which he had won the Fields Medal, which had later was discovered had problems, had errors. And he was convinced early on, he was one of the few early adopters, that it was necessary to formalize in a computer system mathematical proofs in order to ensure the certainty, the correctness of the proofs. But in order to do that, maybe as a second step, you had to design a new foundation for mathematics which would admit such a formalization on a computer. Because you can't just formalize proofs in ZF set theory. If you try to do some advanced homotopy theory, like Voevodsky's Fields Medal work, you'll very quickly run out of patience or facility with ZF set theory. It doesn't work. You need a new system of foundations which will allow you to formalize in the foundations the advanced mathematics that you're doing, and then which will admit implementation on a computer. So there was this kind of twofold aspect, is to capture higher mathematics, but in such a way that you can implement it on a computer. So that was the idea.
Then the interesting philosophical question is, does not it better the question in some sense, make the question in some sense?
In which sense?
In the sense that you need advanced mathematics in order to construct a language, then in some sense is used in order to increase the certainty in. So, okay, so why not?
No.
Okay, why not?
Because the system is Martin-Löf intentional type theory. It's not some advanced mathematics that a Fields medalist made up. He took it off the shelf. And it was originally proposed by a foundationalist, Per Martin-Löf, one of the 4 squares in my first slide there, in the history of type theory. And it was motivated by principled philosophical considerations about the nature of the foundations of mathematics. It's off the shelf, old school mathematical logic.
Yes, but that I understand.
Yeah.
But what you have insisted on is that you added something to this, is that the interpretation. And you say that the univalent axiom follows this interpretation. So what now I do not more understand is whether, to tell it in a very crude way, is whether you're doing semantic or syntax in your proof, whether you're working on the interpretation or you're working in the syntax of the system.
Well, that's always the case when you do
of course.
mathematics. You have an interpretation in mind, but the proofs, the formal correctness of the proofs are controlled by the formal deductions in the system.
So you are saying that the interpretation guide the heuristic of the proof, but not the proof. This is what you are saying?
Well, the proofs are Lückenlose Folgen von Zeichen. It's their derivations in a formal system, completely rigorous, following from the rules of inference. The accompanying intuition in the mind is not part of the, unless there's some kind of.
Okay. But sorry,
It's not part of the proof. Proof is formally correct because it follows from the system, and that's what the computer's checking. That no mistakes have slipped in. I mean, we're talking about Frege here, really. It's the same idea. I have a great quote in it. I'm going to quote myself. I wrote an article, Thierry and I wrote an article at the end of the special year. You can search for it online. called something like Homotopy for Univalent Foundations on the Large Scale Formalization. But here's the quote. Future historians of mathematics will wonder how Frege and Russell could have invented the idea of logical foundations before there were any computers to run them on. How's that? Pretty good.
Yes, but when you formalize a proof within a formal system, you use the axioms or the linear assumption of the formal system. And then, in some sense, the fact that you can write the proof within the formal system is still not a guarantee that you, so to say, you have made a proof of equicertainty with the formal system. That is what you do. I can formalize a proof in piano second order arithmetics, of course, but piano second order arithmetics is still not, in some sense, a foundational system, because if I want to justify the axiom of piano second order arithmetic, I go to set theory. Set theory is a foundational system exactly because I can interpret piano second order arithmetic in set theory.
All due respect to piano, one can write down any garbage. And
Yeah,
call
that's
it a formal system,
exactly the point.
and then you have a proof in that system.
Yes.
It doesn't tell you anything. You could take Serre's spectral sequence proof that pi4 of S3 equals Z, call it a formal system. So what's important is that the system of Martin-Löf type theory is a principled, reflective system created by someone with a philosophical or maybe a foundational justification for the system.
Okay.
And there's a great deal of literature. Per Martin-Löf has a number of essays which motivate and justify and not formally, intuitively justify the laws of the system.
So now the second part.
That's your point, right?
Now the second part of the question.
Yeah.
You say that this is a constructive system, and when you were answering to Eric's question, what I did not understand is this system enlarge the notion of constructivity.
Yes.
So there is something that you can prove in the system that is normally attributed to non-constructive mathematics.
Yes, that's right.
That become constructive.
Yes.
It seems to me that the answer is yes.
Yes.
We
the answer
began
is
with
yes.
action of choice.
The answer is yes, yes. It subsumes a great deal of classical mathematics, like the computations of the homotopy groups of spheres, right, into a system which still retains a computational character and a constructive character.
So in some sense, you're pushing a farther Hilbert program.
Maybe
In some.
I don't want, yeah. Yeah, in some sense, yeah.
There's anything, sorry.
Okay, one go.
So I think I did have a question, but I think Peter was first, and then there was Jose.
Okay, go.
Can you say something about higher reliability?
Oh, I don't know.
We can leave it to.
Let's leave that for later.
Okay.
Next.
Jose?
Yeah, so as in any new foundation of mathematics, there is a recasting of all concepts.
Yeah.
And there should be a justification of this recasting, right?
Yeah.
Now, I have heard from Jonathan many times enough the fact that the S1 is a base point with a loop,
Yeah.
that I feel it almost natural.
Yeah.
But this wouldn't be the case if you tell a classical mathematician S1 is a point with a loop. And then what is the justification? Is the justification that you can compute the fundamental group and it is exactly the same as the fundamental group of the S1 in the classical theory? Is this justification that you can do set theory within this, and then within this set theory that you could do internally, you could express the classical space that is S1 and then compute the fundamental group of that one? What is the justification that the circle is a point and a loop? That's my question.
Yeah, I think it's the homotopy type of the circle.
Mhm.
So it's not the circle in the plane. It's not the unit circle
Mhm.
of all points x, y such that x squared. It's the one. It's the homotopy type. And then the homotopy type of the circle can be characterized with a universal mapping property, just like the integers or the natural numbers can be characterized with a universal mapping property. Let's say it's the unique set with a base point and a endomorphism, right? It's the universal, the initial one. So it's just like if you're happy with that characterization of the natural numbers as the free, maybe structure with a distinguished point and an endomorphism, this is a characterization of the unit circle in the same spirit. It has an initiality or a free property. It's the free structure with a base point and a loop. It's the same kind of thing.
Thank you.
I think that's what. Now,
Yeah, I'd like to go back actually a bit to Marco's question. So, so by the end, you sort of mentioned this idea that the Martin-Love type theory is like a well-justified system philosophically. Then, of course, you're adding to this the univalence axiom.
exactly, yeah.
So one thing that I was curious about is, if you move to like different kinds of foundations, like in set theory, you have this classification which is sometimes helpful. Those justifications that are intrinsic or extrinsic.
Yes.
Extrinsic is about the consequence of your axiom, and intrinsic is about the meaning of what you wanted to define. And so, I guess from your talk, it seemed to me that sometimes you were appealing to some sort of extrinsic justification for univalence when you said that there were some properties.
Yeah, look, we can compute all this stuff.
Right, right. And sometimes also intrinsic, you're saying, when you add it, then the kind of models that you get are homotopy models. So can you say more about this?
Sure, yeah. So the extrinsic justification is like, look, we can prove all these theorems and it fits in with the rest of this mathematics and it has the normalization property. And the intrinsic justification, you would have to go back to what was the intrinsic justification for Per Martin-Löf in the proposing the constructive type theory. And one aspect of that was for Per Martin-Löf, what he called meaning justifications, is that it? The
Meaning explanations.
meaning explanations, that's right, where he explains the different type constructors in terms of what you can do with such a type and how it behaves in the system of type theory. And that goes back arguably to, now we're talking to the philosophers, maybe to Michael Dummett and the verification notion of meaning, maybe even Wittgenstein, with the idea that a logical operation is justified by how its consequences are used in the system and its principles of verification and so on. Philosophical story there about verificationism and Michael Dummett, this kind of stuff. So that school of thought, which Per Martin-Löf is kind of arguably part of in giving his meaning explanations for the type theory, can be extended to univalence in trying to explain why we should adopt the univalence principle now, not as an axiom, but as a rule of inference in the type theory, a further rule which governs the behavior of the universe. In the Martin-Löf type theory, the original theory, the universe is underdetermined. You don't know what the identity type on the universe is. You know what the identity type on a function space is, right? It's two functions are equal if they take equal arguments to equal values. You know what the identity type is on a sigma type. It's pairs of identity proofs. But you don't know what the identity type is on the universe. The universe in Martin-Löf's type theory is underdetermined because you can't say what the identity type is on there. And the univalence axiom answers the question, what is identity on the universe? And the answer that it gives is it's equivalence. It's equivalence of types.
But even for functions, it's underdetermined too, if you don't have general function extensionality.
Yeah, there are still some cited unresolved questions,
But it,
which
but-
are also resolved by univariate.
yeah, so actually univalence implies.
Is more than equivalence, it's topological equivalence. So it's
No,
equivalence.
it's type theoretic equivalence,
Yes, tautological.
which is motivated maybe externally under the interpretation of
Other than
topological equivalence. But type theoretic equivalence is a perfectly sensible notion. Maps back and forth that are equivalent to the identity, the composite of which is equivalent to the identity.
So if I can just
Yeah, please.
follow up on this, so
No, because it's a good question, is why, what is the internal justification of this principle?
right, and I think your answer was very interesting, surprising to me actually, because so basically what I sort of take from what you're saying is that the univalence axiom is about, so if you have this sort of intrinsic justification perspective, right, so you think that by adding these axioms, you are making the meaning of certain kind of concepts in your theory more precise, right?
That's right, that's right.
And it sounded to me like what you were saying is that that makes the meaning of the universe more precise.
Yes.
Do you also think that it makes the meaning of equivalence or identity more precise? Because so the kind of justification you were giving in terms of like connections to like this inferentialism kind of thing, right? So
Mhm.
the idea that the meaning is used, right? So that's like the,
Yeah, that's the idea.
yeah, right. So I could see.
And I'm not asserting that myself.
Sure,
I'm
sure.
kind of saying this is behind the tradition in which Martin Left was working.
So I could actually see, I think, a way, like a route from this sort of meaning is used to univalence if I would have thought that what you are then making sense of is equivalence, right? So you
Yeah.
are saying, you know, what does it mean to be equivalent? Well, how do we use it? And basically we use it as the same as identity.
That's right.
So
You use it by transporting a property from one thing to another, or a structure on one thing to another that's equivalent to it.
right,
You use the equivalence as a bridge across which you can transport structures, properties, statements, and so on.
right. So in that sense, is the univalence axiom about equivalence as much as it's about universes, or is it about
Oh, it's about, I mean, the universe is just the setting in which you can state in type theory property relating to types, because two types are terms of the universe, and then you can build a relation between them. So it's about universes in that sense, but it's about what are the identities between types. So it's kind of, it's a internalization or an implementation, the principle of invariance, that equivalent things can be identified or share all the same properties.
When you say that that theory becomes a particular case, this interpretation, you mean that you can prove the action of set theory within a particular theory? Should become theorem, the action, I don't know, the action of replacement. I don't know, the action of union. You can prove the actions of the theory as theorem of.
You can prove the laws of the category of sets,
Yeah.
not the axioms of Zermelo-Fraenkel set theory. No, that's a different system. But the laws that hold or maybe abstract set theory in the sense that category theory
Okay,
or
okay.
some
okay,
other
okay.
similar system implements set theory where you can identify isomorphic sets and so on. Not Zermelo-Fraenkel set.
But like Levere set theory.
Absolutely. You
So
can
this-
prove,
Levere set theory.
yeah,
Okay.
ETCS, the elementary theory of the category of sets. You can prove that for the zero types in HoTT. That's what it does.
Yeah, another thing that I think this is a subtlety that your U in the univalence axiom is actually indexed.
Absolutely. No hierarchy of them in the
Right,
Martin
because each universe, all the terms of a type are in a universe.
That's right.
And so the identity type has to live at
The next universe up.
n+1.
In fact,
So this is kind of a reflection principle.
Yeah, that's right. The univalence axiom itself, yeah, I better not go outside the line, right? The univalence axiom itself says, maybe, let me write it like this, if I have two types and they're equivalent, then that's equivalent to, did I write id or did I write a?
Yeah, ID, right.
ID. Id over the universe of AB. Right? There we go. This equivalence is between types in this universe, because there they are.
Right.
They're terms of this universe. This equivalence is in the next universe up. Because
Yeah.
these types are in the next universe up. So the whole thing is stratified.
But here's the
But
question.
just like everything in type theory is typed, right?
Right, right.
Everything's typed. So
But if-
there's nothing spooky about that.
No, not at all.
It's just, that's how type theory is. Everything is typed, so.
Yeah, I kind of read this as, like I said, kind of a reflection principle. That
Tells you something about the identity type on the universe gets pushed down
Yeah.
into a relation inside the universe. I think of it as saying that the universe is locally small as a category, if that means
yeah, okay.
something to you. Its identity types are in the universe. So they're all sets. If you think of it in terms of a category, the Hom sets are small.
It's not clear to me that this solves the problem that you claimed this solves, which was that Martin-Liff type theory, the identity types are underdetermined. Because you're kicking them upstairs each time.
Identity types on the universe.
Yeah.
No, the identity type on the universe now is determined to be the identity type on you.
Right,
That-
no, yeah,
that
right.
Sure, term, so A and B are in you, right? And now I can ask, I take two terms, type U, and I can ask, what is id U A B? I don't know. And this tells me something new. It tells me, first of all, it's a type in U.
Yes.
So it determines that that's the local smallness that I was just saying. And moreover, it tells me which one, namely this one. Which is this one, which is there exists an F from A to B, and there exists a G from B to A. And if I compose them up, id of F after G, that's the identity function on, tell me which way the composition goes, A or B.
Yeah.
F after G on B. And id of G after F is the identity on A. So that's a type now inside the universe U.
Mhm.
So it specifies what the identity types are.
Okay, any other questions?
More like,
Yes.
more like maybe half of a comment. Like Martin-Liff type theory doesn't force univalence, right? You can say the undetermined, we can solve this another way and
Yeah.
let's say something else.
Right, no, Martin-Liff type theory doesn't force, it expresses univalence, but you can't prove it.
Yeah, I don't know what I said is you could add another axiom that would contradict this.
That's why when we write it down in Martin-Liff type theory, and we ask, does it hold? Does it have a term? Is it correct? That's up for grabs, right? And that's where Per Martin-Liff originally said, no, that's not good. It's gonna spoil the computation. The normalization algorithm is not gonna go through anymore if you throw that in as an axiom. And that was the accomplishment of Tirico. So first of all, the insight of Voevodsky that it should be correct, if only you can arrange things in the right way, this should still be computable. Computational, it should have a computation content, which seemed incredibly implausible at the time. And then it was the insight of Kokon to figure out how to rejigger the system in such a way that this thing would actually compute and you would still be able to preserve the normalization algorithm with this principle.
So I mean, just with respect to HoTT, you still have canonicity up to homotopy.
That's right, up
So
to homotopy. you have
homotopy
canonicity.
canonicity, which then you can argue, okay, what's a homotopical computer?
Yeah, but that wasn't at all clear. That was the conjecture of Vygotsky, was that you have homotopy canonicity up to home. And that was quite an open problem for a long time. And I think it's, in my opinion, it's still open because the proof that it was announced 5 years ago has not been written down, published, or formalized and checked by a computer, which is now the new gold standard of correctness.
Yeah, I have another question about, so this idea or the justifications of univalence.
Yeah.
So you mentioned that if you look at models of multi-node type theory in which univalence holds.
Yeah.
Well, at least this what you took to be like the standard models of multi-node type theory satisfy that. And I guess my question is there kind of like a converse of that fact that if you have a model of multi-node type theory that satisfies univalence, it is in some sense standard or canonical?
Yeah, there is a sense in which that's true. I mean, it requires some kind of technical padding, but you can build a Quillen model structure. If you take a model of the rest of the theory, in which then you can express the univalence principle for a universe from that univalent universe. So you can express it, and then you assume that the universe is univalent in a sense. From the univalent universe in such a model, you can generate a Quillen model structure, which gives you a homotopy theory on the model. So the answer is yes. Good question.
Okay. Last question.
Okay.
That-
I had a couple, I'll narrow it
No
down.
pressure.
Yes, we managed to get 2 hours, so this is
I
last
would-
question.
Okay, who will ask the question by you?
Well,
Go.
I'll make it more precise. So it has to do with the relation of what you just talked about to structuralism.
Yes.
So Balthazar Grabmaier is about to publish a paper which is an attack on structuralism. But briefly, what he does is he tries to say there are ways to preserve isomorphism in structures, but hive off, sort of separate off decidability. You can take properties that are computable in one system, make them uncomputable, undecidable in another system.
Yeah.
Systems are still isomorphic. And this speaks, and I'd be happy to send you the preprint. Is that possible in type theory, or can you not separate, computability and decidability from equivalence? Or
I think you're using the terms in a different way than I do, because I don't even know what it means for systems to be isomorphic. I know what it means for like structures, like algebraic structures to be isomorphic, but
Yeah.
not foundational systems to be. So just ask me the question again.
Yeah, very compressed.
Yeah, because I didn't understand the basic setup.
Well, let me send you his paper. Let me ask this question. Are there any undecidable true statements?
Undecidable. True. What do you mean by true?
Is there-
Mathematical,
Well, like Gödel undecidability.
like what?
Gödel undecidability.
Natural numbers inside of type theory still has the same character as any formal system of arithmetic. The formal system of piano arithmetic, if you like, can be modeled inside of Martin type theory.
So you can get a Gödel sentence.
Oh, absolutely.
Okay.
As a formal system, it's a finitary formal system.
Sure.
Fine. I mean, there are lots of closed propositions, closed statements that are not decided.
But that seems to be somewhat in conflict with what didn't Martin Luther sort of want verificationism? Like everything is knowable.
No. No.
Oh.
I don't think he had any conception of trying to defy Gödel incompleteness or something like that.
Oh.
Not everything No, in fact, I mean, arithmetic is kind of open-ended, right? So I don't think Paramount would argue with that.
Thank you.
Okay. So we are finished before midnight. Thank you.
Okay.
Thank you very much.